My name is Kevin, and I'm here with Na and Mullen, and we're from PayPal. So we'll be talking about Kafka at PayPal and our journey to enabling 400 billion messages a day. So let's get started. This is the agenda for this session. We'll start with some details about PayPal and Kafka at its present state at PayPal. Then we'll dive straight into the journey with how we began using Kafka, how we experienced a massive growth spurt, which led to various challenges, and the road to overcoming these challenges through Kafka as a service. Finally, we'll end with some notes about what the future has in store for us. So PayPal. In case you don't know, we are a global payments processing company, and we have been growing tremendously over the past few years. I will go into specific numbers here, but you can see total payment volume has increased dramatically year over year. And you might be wondering, what does any of this have to do with Kafka, right? Well, it's all about the data. As we are seeing an increase in payments volume, we are seeing an even bigger increase in the amount of data that we have to process. And we leverage Kafka heavily, so it's very important that our Kafka infrastructure can handle the scale and to grow. So as mentioned previously, our Kafka ecosystem processes 400 billion messages a day. We have over 50 clusters, over 3,000 topics, and totaling 7 petabytes of disk space. We have been using Kafka for a while now, starting with version 0.8, and our current version is 1.1. Our tech stack has also grown enormously over the past few years, with clients using languages ranging from Java to Python to Node.js. We also have many different types of application frameworks connected to Kafka. Gitmo and Scubes are two open source by PayPal. Gitmo is a big data framework that provides a unified data API to access data from storage, such as Kafka and HDFS. And Scubes is a highly scalable asynchronous platform for data processing applications like Kafka. Our Kafka clusters are also multi-tenant, which means each cluster is generic in the sense that there are multiple use cases in a single cluster. And our ecosystem is distributed across multiple regions and different availability zones. Now let's take a look at some data pipelines. On the left-hand side, you will see some Kafka use cases at PayPal. We have user behavioral tracking, experimental data like A/B testing, merchant SLA monitoring, and risk and compliance analytics. So all of these use cases will generate data in the form of a business event, an application log, or application metric, or any combination of the three, right? And this data will pass through Kafka using batch processing or real-time streaming and end up on the right-hand side in framework and platform land, where they will be consumed and used for analytics or other kinds of processing. Now, you can see that there's a double arrow, too, because we have many flows in which there are multiple hops. So, for example, data will go into Kafka, get consumed by a framework. Additional data will then get pumped back into Kafka and then consumed by yet another framework. So we also have some use cases that leverage multiple messaging systems. And it's very common to have multiple teams own different parts of an end-to-end pipeline. So we have seen some pretty complex flows. Now let's take a step back and rewind a few years to the beginning. So when Kafka first started getting popular at PayPal, individual teams very quickly wanted to use Kafka, and they did by setting up their own clusters. Now, this posed many challenges as they were duplicating work, there was a lack of standardization, they were inexperienced with the Kafka code base, and there was no knowledge sharing. So this made it very difficult for them to manage and maintain these clusters, especially as Kafka usage grew. When Kafka became big enough, it was decided that a dedicated Kafka team would be formed to manage everything Kafka related at PayPal. This allowed the application teams to focus on building their applications as opposed to managing Kafka clusters and entire infrastructure. Soon after the Kafka team was formed, we experienced a massive growth spurt as Kafka became more popular. From 2015 to early 2017, Kafka traffic grew dramatically, and we created many new clusters and expanded existing ones. We saw our Kafka ecosystem expand to a massive scale as we onboarded massive new use cases involving ETL, logging, high-throughput metrics. We very quickly went from processing 100 million messages a day to 1 billion messages a day to 100 billion messages a day. And it was a very exciting time. But as we rapidly expanded, we began to encounter various challenges. The first challenge was that everything was manual and bare metal. We didn't have automated tools to do simple things such as set up a new broker or set up a new mirror maker. So operational work took a long time. It would take up to months sometimes to onboard a new use case, especially if new hardware was required. Second challenge was that we had no visibility into cluster health. Sometimes a broker would be down, and sometimes we wouldn't know until a client told us they couldn't produce or consume. So the TTD, time to detect a broker failure, would be up to 24 hours at a time. Third challenge was that when issues happened, it took a long time for engineers to debug and resolve these issues. The TTR, time to recover, would range anywhere from days to up to a week sometimes. And this was especially a nightmare when our engineers were woken up in the middle of the night to debug cluster issues. Many times the solution was just simply to do a simple broker restart. And the final challenge was that our software engineers were finding it that they spent more time doing operational and support work as opposed to developing software and building applications and services. So, yeah. In order to overcome these challenges, we decided to create a plan and to tackle them in iterations. Our first goal was to provide an operational dashboard and to improve client visibility. This led to our first important project started in 2015, Kafka Mon. So Kafka Mon is our monitoring and operational dashboard that enables both operators and clients to view and manage their Kafka components. A few notable features are the ability to view the status of any component, to create, modify, and repartition topics, to deploy and manage brokers, zookeepers, and mirror makers, and to view the logs of any of these Kafka components. So all of these functionalities are available through a user interface, so people don't have to SSH into a host or run custom shell scripts just to do things anymore. So after developing Kafka Mon, we decided to shift the focus to the client side, as the challenge we had was our clients would come to us and ask us about how well their applications were performing, and if they were performing at all. They would ask us questions like, what is my availability? What is my latency? And we would be unable to answer these questions because there's simply no good way of measuring these from just the server side. So additionally, we couldn't really detect client issues before they reported them to us because many client issues are isolated to the client side. So when we looked at cluster-wide health metrics, there was no indication of an issue happening at all. So this led to a drift between the availability and visibility of the clients and the servers. So we had to fill this gap. To fill this gap, our solution was twofold. First thing we did was we created a canary application that periodically sends and receives heartbeat messages to all of our Kafka clusters. So this canary application serves as sort of a baseline or a sanity test application in which if we notice something wrong with the canary application, then there's likely something wrong with the cluster that it's connected to. Second part of the solution was to create a monitoring interceptors library that gets attached to all of the clients to retrieve and publish client-side metrics. So we also created a custom availability metric that gets sent alongside other JMX metrics, such as latency and throughput. And all of these client-side metrics are sent to a time series database where we have alerts configured and set up to notify us when things go wrong. For example, availability dropping. So all of these client-side metrics are also available through various screens on our Kafka Mon dashboard. And today we have over 4,000 clients monitored by our monitoring interceptors library. So this is a quick screenshot of an application page. You can see the top portion includes a few graphs about metrics like availability and latencies. And the bottom portion will list out all of the clients that are a part of this application. So all the producers and all the consumers and some of the interesting metrics like availability and latency. And all this data is being fetched from our time series database. So with these two things, the canary and the monitoring interceptors library, we were finally able to get a view into the client side. But our clients still asked us about the most fundamental question in any messaging system, and that is there data loss? So I will be handing this off to Na, who will be addressing this age-old question.
Thanks. When we have flows where messages pass through multiple clusters, how do we know if all the data has reached the destination, especially when outage happens? This is the question our customer always asks us. To answer this question, we need to record all the message count of both producers and consumers. In batch case, we can measure the total message count on both sides for each run. Streaming, however, is more complex. In streaming, we need to split the counts into time-based batches. Based on this idea, we build our data loss auditing system. Now let's do a deep dive into the architecture of this data loss auditing system. The data loss auditing system uses interceptor to measure the total message count produced and sent in each time bucket. The interceptor will send audit message to our Kafka topic. The audit message contains the total count per each time bucket, and also some other metadata information, such as cluster name, topic name, and the Kafka client type. All those audit messages are consumed by our data loss auditor streaming application. The auditor will catch and aggregates all the message count of both the producers and the consumer, and then compare them to decide whether there's a data loss or not. The data loss auditor will, if there's any data loss happen, the auditor will send a data loss alerts to PagerDuty. The PagerDuty is an alerting system that we use to receive alerts. In the meanwhile, the auditor will send all the counts of their time series data to Elasticsearch, and then so that we can view the data loss through our Kibana dashboard. Let's take a look at the data loss tracking dashboard. The blue line here shows the total message produced by producers in a time period. And the orange chart shows the total number of messages consumed from the same topic by a consumer group. If those two charts matches, this indicates no data loss happened. If the total number of messages consumed by our consumer group is less than the total message produced to this topic, so you see here there's a gap. This indicates our data loss is detected. However, I would like to mention, by only using the message count to measure data loss is difficult to achieve 100% accuracy. Two reasons. First, sometimes the duplicate message delivery could happen in certain scenario. Second, the message delivery could have delay. In this algorithm, we wait for a certain time for all the message reach to the consumer side. So if certain message get delayed, we will consider is a data loss. Even though this algorithm has some limitations, but this lightweight algorithm still gives us some insight about the data loss in our data pipeline. It's very useful. So far, we have already talked about Kafka Mon, KPI dashboard, and the data loss auditing. All of them build a strong foundation for our cluster and the client visibility. However, with more and more customer on board, some of our clusters are getting overloaded, which impacts availability and the latency. This led to our next goal, onboarding and the capacity management. Before I talk about customer onboarding, let me ask you guys a question. Has anyone suffered from onboarding a new Kafka topic in production environment? You can raise your hand if you have trouble to onboard a new topic. No? Okay. But in PayPal, since we have so many customers are using Kafka, we cannot allow customer to create a new topic silently and then start to publish data to the topic. We have to control the topic creation carefully so that we can make sure our cluster will have enough capacity to support the customer need. So let's take a look at our old onboarding process. The customer has to file a Jira ticket to onboard a new topic. They have to put some basic topic request information, such as topic name, cluster name, message size, retention period, etc. Then Kafka team review those tickets and do capacity assessment manually. If capacity is okay, we'll create topic and then notify customers by marking the ticket status as complete. Due to the cross-team communication and the manual capacity assessment, This process was extremely slow. It usually takes days to weeks for a new customer to onboard a new topic. This was not acceptable. We then improved this process by providing self-service onboarding. So in this self-service onboarding, we provide a web-based user interface. Oh, sorry. Customer will register the use case and fill in the topic request information through this UI. By submitting the request, the capacity assessment will be automatically done, and also the topic will be automatically created. This automated process helps us to reduce the customer onboarding time from weeks to minutes. Here is our self-onboarding UI. We take all the customer information through this UI. Next, let's talk about capacity management. PayPal has one of the largest Kafka deployment in the industry. Every year, we invest tens of millions of dollars in hardware to build Kafka clusters to serve our customer need. How to control the hardware cost and reduce the management cost become one of our challenge. So capacity management will be very important. So in the past, we allocate cluster capacity on a per cluster basis. We usually assign our dedicated cluster to our big use case or our dedicated organization. As time passed, some clusters are getting overloaded, while some clusters are underutilized. In addition, this dedicated cluster model also made it very difficult to share data between different organizations. We then improved this by moving to our cluster group model. In this new model, we treat all the clusters in the same data center as one group. Our new use case can be onboarded to any cluster in the same data center group. So you can see this new model makes it easy to share data and capacity among different clusters within the same group. It also enables load migration between clusters. For example, we can move our topic from one cluster to another cluster in the same cluster group and allow the traffic to this topic keep growing. Now, with this cluster group model, the Kafka usage of one organization can spread across multiple clusters. To better understand how the clusters are getting used, we further build our capacity showback model. This capacity showback will calculate and display the capacity usage for each organization and the customer. So by seeing all the capacity usage by different organizations, we can know who used the capacity the most. That way, we can better manage the capacity usage. And also, this model builds our foundation for our pay-as-usage. So now let's take a look at the capacity showback. On this chart, it demonstrates the network the disk usage of one organization in a specific time period. On the right side chart, it demonstrates both the network usage and the disk usage among all the organizations. Now we can see Tushar's organization used most of the network usage and the disk And in the future, we will send different bills to different organizations based on their hardware usage. So next, I will hand over to Marlene to talk about how do we migrate loads between different clusters by using our configuration service.
Thank you, Na. So why we built all these capabilities mentioned before, we still had concerns around utilization of our clusters and few of the availability challenges that we had in order to maintain high availability for all our clusters, topics and clients. So let's first look at cluster utilization. So as we mentioned, we have multi-tenant clusters, and different growth rates of various clients in our multi-tenant clusters resulted into uneven utilization of our clusters over a period of time. Also, some of the clusters that we set up initially started to grow old in terms of machine configurations, and we needed to decommission them. Now, in order to do the utilization better for our clusters, we have to move the topics around the clusters, right? And in order to move the topics around, we have to make sure we create the topics on a different cluster with the same configuration for all those topics, having same retention period, same partition count, all that. And we have to make mirror maker changes accordingly. And last but not the least, we have to make changes on the client side to be able to use new cluster. Easy, right? Well, not so easy if you have to make it repeatable. And the biggest challenge today in having the client use the different cluster is that today the clients depend on a specific cluster via bootstrap servers in their code or configuration. And we have polyglot base of client. So some clients are in Java, some are in C++, some are Python, you name it. And this makes it very difficult for us to manage the client movements. However, before we talk about the approaches we took in order to address these challenges, let's talk a little bit about few availability challenges that we had. For example, one of the challenges we had was based on the Kafka client and the server-side versions we were on at that time, a couple of years back. Some of our Kafka Java-based producers started to experience batch expiration errors. What are batch expiration errors? Anybody? So let me tell you. So in Kafka, the Java client for producer batches the messages before it is sent to the brokers in order to utilize the networks better. Now, when those batches cannot be delivered to the brokers, even after all the producer retries exhausts on the producer side, they are expired based on the number of retries, and beyond certain time, if it cannot be delivered, then it will mark as expired. This resulted into 0% send availability for those producers on those topics on those clusters for us. Now, while we wait for doing the root cause analysis and all that stuff, we could not block our clients. And in order to keep them running, what we had to do was move all those topics from one cluster to the another one. And here in the example is just one topic, but in reality we had like about 10 or 20 topics, for example, right? So we had to move all those topics from one cluster to another, make all the required mirror maker changes, and then give them the new bootstrap servers which they use to change their code or config and do the live push. The other challenge that we faced was sometimes the network switch or power outages resulted into close to 0% availability for the whole cluster. And all of our client applications on that clusters will be down, basically. Here, the additional challenge we face is, apart from the challenges we mentioned before for topic movement, is we lose the access to the cluster. And when we lose the access to the cluster, we don't even know what topics were there. How do we even recreate the same setup on a different cluster? So this posed bigger challenges for us. Now, while we tried to fix all of this manually, and sometimes we had long hours obviously, it meant several days and hours of downtime for our clients. So we decided to do certain things. One, we decided to make sure that we have metadata about our ecosystem, which includes our clusters, topics, clients, and their relationship, because that metadata can allow us replicating and recreating the same topics on different clusters using that metadata. So in case of like complete cluster unavailability, we could still survive. Second, we wanted to break the client's tight coupling to the clusters. That happens via the Bootstrap servers. So we decided to abstract our clusters from clients. And three, we decided to have operational ability to easily move topics around, which will take care of all the topic configurations and mirror maker changes. So let's first talk about a configuration service that we built in order to abstract our clusters from the clients. Here is how it works. So client applications, instead of depending directly upon the Bootstrap servers in their code or config, they will use this configuration service to make a call with set of topics they are interested in order to do produce or consume. The configuration service will do a lookup on the metadata that we built for our having all the clusters, topics, and client information, and ultimately it will give the Bootstrap servers where those topics are located, along with other Kafka client-side properties we return from configuration service to the client app. The client application will use these Kafka properties to create their Kafka objects, client objects, and then further do read and writes on our clusters. Now here, as you notice the PayPal library box here, the client applications which are on Java and Scala stack, they use our PayPal client-side library in order to make this configuration service call. And it allows us controlling the configurations on client side, it allows us standardizing them and enforcing those configurations on client so that we can avoid client-side configuration issues. Like for example, sometimes we used to get cases where like producers will configure their system with X0, and then when they have connectivity issues with clusters, they will start losing messages and they will come back to us and file like top priority bugs saying Kafka is losing messages, for example, right? So we had a lot of these misconfiguration issues that we wanted to nail down. So this really helps us in that. Now while the configuration service helps us abstract clusters from our client, the admin service in the control plane helps us run the operational commands on our data plane components. Like, so for example, end to end, if you want to move the topics from one cluster to another, here is how it will work. We will trigger commands on our admin service, which will make sure that the topics configurations are retained when and it is created on a different cluster. It will make all the required mirror maker changes, and then based on our metadata, we coordinate with our clients to do application restarts. And upon the application restarts, they will get, they will again have a call to configuration service, which will give them a new Bootstrap servers of those topics, and they are on a new cluster now. So with all of these improvements, we went from our old manual, error-prone and unpredictable process, which resulted in several days and hours of downtime for our clients, to automated, streamlined, predictable process, which brought downtime to like few minutes compared to several days. So this was a big improvement for us. Now let's talk a little bit about Kafka control and data plane. So here, as you see, there are two sets of clients that come to our presentation layer, admin and clients. Admins come to the presentation layer in the control plane in order to perform tasks such as creating new mirror makers or creating topics or doing topic repartitioning, for example. The other clients come to the presentation layer in order to onboard their new use cases into Kafka ecosystem, or looking at their KPIs, for example. And the role-based access control in the presentation layer allows us separate between two of the clients. Next, we will talk a little bit about few of the components here in the control plane. For example, the admin service. The admin service helps us run commands on our data plane components given our network and deployment topologies complexities, involving restrictions on firewall and restrictions around, security restrictions around what can talk to who. And admin service simplifies all that for us. So we have one place to go to run commands, and regardless of where the command needs to be run, it will take care of it. The mirror maker management component helps us automate few of the tasks for mirror making, where upon the topic movement we have to make mirror maker changes, set up and analyze the capacity of mirroring, and also of course creating new mirror makers. And as we mentioned before, the configuration service helps us abstract our clusters from our clients. Next, we built set of APIs over this functionality in the control plane components. And these APIs are not only accessed by our presentation layer in the control plane, but they are leveraged by other ecosystems in PayPal having Kafka needs to further automate their system. And last but not the least, that our access to the data plane components is restricted to only the components in the control plane. Why is this important for us? Because as earlier we mentioned that we built a Kafka Mon, right, system, and that system used to run on like a couple of boxes, and in order to perform admin operations from those boxes, we had to open up connections to like all the clusters that we own, and that was not allowed internally from the networking perspective and all that. So with all of this heading to the future, we would want to focus on automating the client failovers. If you remember, we talked about that when we have to move topics, we have to coordinate the application restarts with clients, and that's not the ideal world to be in. So our next step is to automate it so that automatically the clients can restart themselves when the configurations of topics where they are hosted is changed. We also want to automate some of the remediation processes that we do today and contribute back to the community in terms of these features like client-side KPIs that we talked about before, and share our learnings and experiences through forums like this. So what's the conclusion of all this? So today we talked about the challenges we faced running Kafka at scale at PayPal. We hope that you feel that how running Kafka without proper tooling can really become unmanageable in the long run. We also hope that you realize the work ahead of you for making Kafka work at your environment, dependent upon the size and the structure of your organization. And lastly, we sincerely hope that all these approaches and the ideas we discussed here are good templates for your thoughts, and you do take them up to the extent applicable to your use cases and make them work for you. With that, I would like to thank all of you for your time, and now we can take any questions if you have.
5 minutes for questions, so I know there's lots of questions, so can you speak loud?
I can try to repeat.
Yeah, the throughput that you're talking about here, like what happens if one consumer dies and you have a huge backlog? How does your backlog processing look like? Do you bring up just a separate cluster or a separate instance to process the backlog while you are actually processing the current traffic, or how do you?
So let me see if I get your question right. You are asking that if one consumer group dies,
Yeah.
what happens to our system?
Yeah. How do you catch up? Like you then, like one consumer group dies and your client is like really has huge backlog.
Right.
Because with this throughput, you like even in
Right.
Tuesday,
Right.
you can.
So what we do is as we mentioned before, we have the monitoring library that we put in the clients, right?
Yep.
And that library allows us to track the heartbeats of those consumer groups, and we do alerting on that. So essentially, as soon as consumer heartbeats go down, we start to get alerts, and it notifies the owner of those consumer groups that you have a problem and you better take an action on
Yeah,
that.
like you have 10 minutes down.
Right,
Yeah.
right.
By then you will have a huge backlog already.
It depends. Like not all the clusters and all the topics have same throughput, right? So it depending upon the consumer. And typically, what I've seen is very high throughput topic, and the consumers of those are more likely to say that we are okay to lose some messages and restart from latest offsets versus like kind of worrying about 5 hours back, for example.
So offset management, rewinding and forwarding, do you have like I see you have a lot of tools. Do you have like separate tools for that as well?
Not very specific tools, but yeah, we use some command lines to reset the offsets for consumer groups, for example.
Yes. Do you use a special tool for partition reassignment? Because right now the way we do it is really kind of
Right. So it's a very interesting question. So yes, so what we do is we have optimized plan that we figure out based on partition. So we take the Kafka's repartitioning plan, we further optimize it, and then run it through the system. So for example, we make sure that we don't end up moving too many leaders around. For example, it's just one example. So.
Two quick questions. Do you use any kind of centralized schema registry?
So we do have schema registry, but not owned by our team as such. From an infrastructure team standpoint, no.
And second question, if a customer wants to create a topic, lots of options, and you don't have capacity for that, what happens?
So when you don't have a capacity for that, for a topic, what it would mean is on a particular cluster you may not have a capacity, but on some other cluster you may have a capacity. So within a data center, as long as you have a capacity, that's where our abstraction helps us, that we don't want to tie clients to the clusters. As far as within the data center we can manage capacity, we'll put new topics on those, for example.
Apache Pulsar, isn't that the move to Apache Pulsar?
So what's that?
Isn't it the time to move to Apache Pulsar?
I wish I could do that by doing this, but unfortunately not. It will take a while, I think. So basically network bandwidth. So the question is like what metrics we use for capacity management, and it's essentially the network bandwidth and storage requirements. And then we know our cluster's current storage and bandwidth usage, and then based on that we tied them together. All right, thank you all.